Right, thank you very much, ladies and gentlemen. So our next presenter is Ms. Irene Nandutu. She's currently a PhD candidate at the Rhodes University. Her work focuses on applying artificial intelligence to road ecology with a keen interest in mitigating wildlife vehicle collisions. She's currently working under supervision of Dr. Marcellin and Dr. Patrice. Her interest lies broadly in the field of artificial intelligence with a focus on developing sustainable solutions with a high social and environmental impact. We look forward to your presentation. A round of applause.
Thank you for that introduction. I'm going to take you through some of the work that we're able to do, an error correction framework that we're working with time series to model and predict on South African dataset. So I will take you through the objective of the work, the data collection, the results and conclusion. So basically within this objective, we were looking at trying to analyze the current models that are being used to predict roadkill, and ecologists are using what they mean species distribution models. We also developed mathematical framework that are using matrix formalism. And the reason we did that is because of its computational capabilities compared to their functional form. We also able to explore the error correction framework, and the same work also compares the performance of the different linear models. And here we focused on Sarimax only model because it also uses some form of seasonality within it. It's something that is more affected with animals. We also used LSTM and the error correction framework. I'm basically going to focus on two objectives, that is the third and fourth. And in case this sounds interesting, you can look up for our paper that has most of the details in there. So we requested data from Endangered Wildlife Trust, a company in Joburg that majorly collected this data from January 2011 to 2012. They collected it from Mpumalanga province, and our interest was majorly looking at the roadkill count, which are the endogenous variables that we considered, but also the exogenous variables. Those are the three ecological seasons of South Africa. The data basically had different species, which are in classes like Mammalia, aves, Reptaria, and other classes are unknown. So looking at this season, that is the hot, dry season, you realize that aves, or the birds and mammals and Reptaria are being killed more. And generally, when we look at all the three seasons, we are attributing that birds and mammals are killed more on roads compared to other taxa because of their activity behaviors, like the way they engage in social groups and looking for mates, food, and etc. But also we see that most of these animals are killed more in protected areas than other areas. Like when you look at those sampling points, you see that they're concentrated near some form of a certain protected area. For hot, dry season, you see that birds, reptiles, and mammalia are killed more in hot, wet seasons compared to other seasons. That is for these kind of taxa. And we also attribute it to their metabolism costs, given that foods are scarce in cold, dry season, so they don't have enough energy to navigate around and finding themselves to the roads. So you realize that in cold, dry season, we actually do not have any amphibians that are being killed, because amphibians are basically ectotherms, and that means that they are more active in wet, warm seasons than the other seasons of the year. So using all this, for someone who is interested to work to develop matching algorithms, they can be able to design matching algorithms that can be able to detect or predict which type of animal might be killed on a road in a certain season of the year in South Africa, if such data is good. So the data that we used is majorly count data. We selected these taxa. Some of them are classes and others are genus. Sorry, I'm getting familiar with the terms of the ecologists. So for the mammalia, we have 300 entries that we were able to record. Reptaria is around 477 and etc. You realize that we had very less entries within there. So what we did is, so for the days that they didn't capture any record, it doesn't mean that there was no roadkill that was recorded, but it doesn't mean that animals didn't die that day, but it only means that they didn't record a roadkill. So we resampled the data, and for each entry that we didn't have any data recorded, we had that entry as a 0 to be able to have it as a daily data. So because of the existing species distribution models that ecologists are using, some of the challenges these models are experiencing is the failure to predict on small data samples, but also when they're sparsely distributed. And also one of the challenges they experience is if they have limited exogenous variables. Now there is this model called SARIMAX, or seasonal to regressive integrated average. It's a linear model that is very good at capturing or predicting on small data sets, as small as even 50 entries. It can be able to do that. We also have the power of LSTMs. These are nonlinear model that is capable of learning long-term dependencies. Now, these two models, we also realize that because of animal behavior and the idea that they have this form of non-linear patterns, we feel that we want to try out with the error correction framework, compare these two models and see the performance of how they are able to perform. So for any time series, we can decompose it as that it has linear components and non-linear components, but also the error part of it. If we passed any time series within the filter to filter out the noise, we shall have the linear and non-linear components. If we pass the filtered data within the linear, the linear predictor over here, we shall be able to get only the linear predictions. This is the error correction framework. And if we get the filtered data here, where we have filtered out the error and we subtract from the non-linear components within the data, we shall get the residues. And these are the residues that we are interested in. And then we pass it through the non-linear predictor to be able to predict the non-linear components. Now, for any series, even after predictions of our series, there will always be some mode of noise within the data. But we're seeing that. So for any series, if you're dealing with ARIMA models, it has to be stationary, which means that we have the mean and variance. They don't have to vary with time. So the first step that we made sure is to test if the series was stationary by visualizing the collerogram. I'll take you through that. And then another thing is we also had to test the ADF statistics should always be smaller than the critical values or the p-value at either 0.1 or 0.05 and 0.001, because we had 6 taxa, so in here we ended up considering those that if a series was stationary and met any of these, we had to consider that for modeling and prediction. The other challenge that we found here is all our endogenous variables were stationary, but the exogenous variables were not stationary. And because we had less of the exogenous variables, we could not consider any other, but we had to go ahead and make prediction, which could also have affected the performance of our model. Now, for any model that we found that was not stationary, we had to induce tensionarity before we continue. And one of the things that we're looking at is one of the evaluation metrics was alkaline information criteria. The less the value, the better the model order. So talking about model order, so ARIMA kind of models usually. So here SARIMAX has 2 components. The one is this non-seasonal component and the other is the seasonal component. When we look at this is the autoregressive part. This is the differentiation of the moving average. This is the how can I say this? sorry, this went on off my head. But then we also have, it still captures this for the non-seasonal component. And also this S term is for seasonality. And in this case, our seasonality is 3. Okay. So this Q is a moving average. So we used SCF and PCF plots to be able to extensively capture the model order. However, because there was a lot of overfitting, so the higher the values that we capture for these, that is P and Q, the more prone the model to overfitting. So one of the things that we ended up considering was to use an auto-RIMA function, which gave us what I talked about as the less AIC. So when you talk about choreogram, we had something plots that looked like this when we're looking at model orders. So in here, for any, if we want to attain an AR model, so this part of the, this part, the AR, usually we should have some form of a slope with SCF, and also we should have a cutoff from this side. For a RIMA part, which is the first part over here, forgive me, I'll be this other part of this, then in there, when you have to see that there is some form of a slope that is coming here, and for any lags that lie within the error critical section, they are not statistically not significant, so we never considered them. And then when we look at, for example, this, if we want an AR, we really see that the AR1 over here is very high. It's really that sharp, and that is for the other. And if we want to get the Q term, this has to be sloping. That is the PCF, and then we shall get the lag from this side. Now, when it comes to the seasonality part over this side here, that is over this side seasonality, it works more or less like this. But then here, it's not obviously that 1B is the first lag. The 1B is the first seasonal lag. So in here, our 1, if in case that is 1, 2, 3, that will 3 will become lag 1. And when we come here, we can consider, but then this, you may not, it may fail even to model. You really see that it's within almost the error criteria. So you might find that our next lag will be around here if we're looking at the seasonal part of it. Now, when we used this approach, like I said, we were not that very successful with it. That's when we used the auto-RIMA function, and we had things that look like this called the model order. And the less, the better the model. So you realize that this was the best. So smaller AIC means lesser information loss, and the higher AIC means that bigger information lost. So we're trying to, as much as possible, to consider model orders that had the lesser AIC. Now, when we made predictions using only model or the linear model, whatever that happened over there, if we remember, our error correction framework was the residue. So this kind of residues, like I said, anything that is within the error criteria section is statistically not significant, and a RIMA type of models cannot be able to make predictions on it. So we got this residue and passed it with LSTM to be able to extract or make predictions on the nonlinear components. So our findings are SARIMA only model did not outperform any of the models. So you won't see, I didn't put the results over here. But then we have some of these models, like EVS, we see that SARIMAX LSTM was the highly performed model. And then it's also correlation coefficients was high when we look at the actual and the predicted. When we look at mammalia, also we see that SARIMAX LSTM, the hybrid, performed better. When we see that Reptaria, we see that LSTM performed better than this, and I'll be able to explain why that is to the next slide. And then when we see this taxa also, we see that these were able. So there are situations where you see LSTM performing better, and there are situations where we see SARIMAX only performing better. This is how our predictions looked like for the actual on SARIMAX only for each taxa. We extracted only 4 to fit on the slide here. For each taxa, you really see that there is a lot of, the predictions are not that good. when we come. So this is the error that we passed in our nonlinear model to be able to extract this. And what happens here, we have what we call the predictions from ARIMA plus the predictions from the error in ARIMA. I don't know if that makes sense, are the results of this. So you realize that at least we're able, compared to the first slide, we're able as much as possible to minimize the error or make the predictions more accurate. When you look at LSTM, it's also quite performed very well. If you look at like this taxa, you really see that it performed more better compared to even the hybrid model. If you look at this mammalia, you could see that perhaps it also performed more better here, but some cases it also struggled to be able to perform. So our conclusion of our results is whenever the linear components were more than the nonlinear components in the data, the Sarimax only performed better. And whenever the nonlinear components were more than the linear components in the data, LSTM only model performed better. And we attribute this to the inability of Sarimax only model to be able to detect seasonality on residues. We attribute that, but also because we couldn't argue that the data is less when LSTM is doing, but also the inability that it couldn't predict that, then hence it is failing to be able to minimize the error. But also the insufficient data set that we have, you realize that we are having as little as 69 records or 300 records. Those are good for Sarimax, but for LSTM, the more the data you have, the better your predictions that you could get. Another recommendation that we kind of say is this is a very promising technique, but collecting bigger data sets would be a better option in especially increasing on the prediction accuracy of these models, not only data sets, but also going further to collect more exogenous variables because they help in the prediction of this series. Because here we had only 3, we couldn't even get more of them to be able to test and see which one works better than the other. Yeah. And also, in addition, further exploration on how to deploy these models to clients, especially error correction model is one of the suggestions that we have. Thank you.
Thank you very much, Irene. It's fascinating to see the application of artificial intelligence in these wildlife situations and how it can actually benefit not just us, but also the wildlife in itself. It's truly inspiring as well. So thank you for the work on that. On behalf of the RISA, I'd like to give you this little gift to say thank you for your presentation. And then please remember to write down your questions after the next session. We can answer questions for the different presenters. Thank you very much again. I appreciate that.